All right, this would be a quick little mini lecture on how to simplify radicals. And again, I'm going to go fairly quick here. Be sure to pause if you ever need to, and to revisit any of these topics. All right, the square root of 16 is 4, and that's the reason for that. It's because 4 squared equals 16. Maybe you haven't seen this, but this is the cube root of 8, or the third root of 8, and that answer is 2. And that's 2 because 2 cubed is 8. And then finally, the last example here, the fourth root of 81, that is 3. And the reasoning behind that is, it's because 3 is what you bring to the fourth root to get to 81. Really quick, let's review this. These are radicals. This symbol right here is called the radical symbol. And then each of these radicals have what we call an index. The index is very important. In this bottom one, the index was a 4. In the middle one here, this is a 3. And with the square root, our index is a 2. So very important, if you have a radical, you don't have an index, you always assume 2. Those indices refer to the exponent that they're trying to use. So again, in this first example with the square root of 16, you're asking, what would you square to get to 16? And the second example was, what would you take to the third power to get to 8? And then finally, what would you take to the fourth power to get to 81? Those are the questions that we're trying to answer with radicals. Alright, and we quickly now move to variables or exponential expressions. In this first example, I want to take the square root of x to the 6th. The answer to this is x cubed. We answer this in the same way. The question that we were trying to answer was, hey, what would we square to get to x to the 6th? And again, this answer is x cubed. And that is because we have our rules of exponents, that when we raise an exponential expression to an exponent, we multiply the exponents. In this next example, the cube root, again this index of 3 is important, and this index here was a 2. But we're looking for the cube root of y to the 12th. That answer is y to the 4th. And that's because if we took y to the 4th, and we raised it to the third power, we would get y to the 12th. Alright, this brings us to a very, very important property of radicals, and it goes like this. The nth root of an exponential expression, or x to the m, is x to the m divided by n. Meaning, to find each of these answers, these simplified versions of these expressions, I take this exponent and I simply divide it by this index. That's where I get my 3. In the second case, I took the 12, you divide it by the 3 to get the 4 here. And the reasoning for that is because of this property we just talked about. Over here, that when I multiply an exponential expression, or I raise an exponential expression to an exponent, in this case 3 to the third squared, I multiply these two exponents together. And because that process is multiplication, it comes that to go backwards, you just use division. Alright, now I'm going to put these two thoughts together from these last types of examples with numbers and variables, and give us, we're going to use one more very important property, and it's the product rule for radicals, and it looks something like this. If you have two things being multiplied inside of a radical, you can simply evaluate each of those factors separately. That's really important. What that means to our lives is that in this example right here, where I have the square root of 16 times z to the 8th, is I don't have to spend time in thinking about all this at one time. I simply can think about the square root of 16 and the square root of z to the 8th, which we've covered in these last examples. The square root of 16 is just 4. The square root of z to the 8th is z to the 4. Okay, and again, I know there's a lot going on there, but I'm going to move on to some bigger, nastier examples. Alright, What we know so far is that we can take the root or the radical of each factor individually. So now when I look at this, the 64 x to the 9th and the y to the 15th, I can take the cube root of each of those factors separately. I won't write that out though. I'm just going to show you how I would do that at this point. My first thing is I have to know what the cube root of 64 is. I've done way too much math in my life, and I know that 4 cubed is 64. So the cube root of 64 is 4. The cube root of x to the 9th is x to the 3rd, or x to the, raised to the 3rd power. And that's because I took the 9 and divided it by the index of 3. And y to the 5th. So again, I could have written a separate radical for each of these factors to show that, but it's important to show that I can simply just evaluate each of these factors separately. At this point, I want to take just a minute here and to talk about an alternative way of solving this. This is really important. If you're any good with prime factoring, you can do a beautiful thing at this point. And prime factoring is taking a number like 64 here and writing it as the multiplication of primes. In this case, 64 is 2 to the 6th. Okay, I'm going to show you why that's important. So up here, I'm going to attack this problem again. The only difference is, instead of 64, I'm going to write 2 to the 6th in its place, then x to the 9th, and y to the 15th. What's beautiful about this, and using 2 to the 6th instead of a 64, is now I don't need to treat the numbers and the variables differently. I'm just going to treat these all like exponential expressions, meaning that when I take the cube root, again this is the index of 3, I'm going to divide each of these factors' exponents by that 3. And so in this case this would be 2 not to the 6th, 2 squared. The x to the 9th would become x to the 3rd, and y to the 15th becomes x to the 5th. And you can see then, if I wanted to clean this up, what I would do is I would actually take 2 and square it to get 4, which would give me the same answer as I had before. The final real question to ask is, that's all well and good, but what happens if I have exponents that aren't divisible or not multiples of my index? In this case, I have this index of 4, which doesn't divide the x to the 5th and the y to the 10th nicely. I'm going to show you how I'm going to attack this, and I'm going to use the method of prime factoring because I just think it makes my life a lot easier. So I'm going to rewrite this first as the 4th root of 32 is 2 to the 5th, then x to the 5th, and y to the 10th. What I'm going to do is each of these factors that don't have exponents that work nicely with my index is I'm going to separate them into 2 factors. One of which works really nice with my index, and the other part is what I would call the remainder. And so in this case right here, let's say 2 to the 5th, I'm going to write as 2 to the 4th times 2. Again, this is just a fancy way right here of writing 2 to the 5th, but importantly is this exponent of 4 is divisible by my index of 4 and is going to play nice. What I'm looking for is the biggest multiple of my index that's less than my exponent. This x to the 5th actually would be exactly the same. I'm going to write this as x to the 4th times x. Again, that represents x to the 5th. And then this y to the 10th, I'm actually going to write as y to the 8th times y. And this represents, oops, not y, that doesn't make any sense, y squared. There you go. There's 10 y's. So I'm taking the 4th root of all of that jazz right there. Okay, it's important to remember that these parts, the first parts of all of these were the nice parts, and then the other is the leftover. The 2 to the 4th, the x to the 4th, and the y to the 8th are going to play nice with my 4th root. The 2, the x, and the y squared don't. What I'm going to do is apply the product rule of radicals as discussed later, where I can break this radical up. And what I'm going to do is group the stuff that plays nice, in this case the 2 to the 4th, the x to the fourth, and the y to the eighth, I'm going to group that under one radical. And then in the other radical, I'm going to put what I call the remainder factors. Is I got 2x and y squared. So again, all I've done are taken these, what do I have? 6 factors here, 3 of which play nice over here, 3 of which don't play nice, and they're over here. My final step is to actually take the fourth root of the stuff in the left radical, the stuff that works out nicely, and I'm going to leave the stuff in the second radical, alone, because I can't actually take the fourth root of it. And so the step here is take the fourth root of 2 to the fourth, that's 2 to the 1, or just 2. The fourth root of x to the fourth is just an x. The fourth root of y to the eighth is y squared. And I leave, as I said, this second radical all by itself, not changing anything. And there, as quick as it possibly could come at you, is how you simplify radical expressions.